back. Sketch the graph of the function f to determine the type of discontinuity. Okay, you see some of these you can sketch, but this probably is something you're not familiar with. These three are okay. First one is a parabola, second is a constant, third is a line. Sorry. This one actually requires some calculus to be able to draw. And this is, well, while not too bad, it still takes some intuition to draw. Okay, but let's see what's going on here. First one is a parabola to the left of -3. Second one is constant just at some number. Okay, the third one is a line, part of a line from -3 to 0. From 0 to 3, it is a rational function. 3 onwards, it is some other rational function. So you see the cut points are -3, 0, and 3. So they are saying that these are discontinuous. These are points of discontinuities. What type of discontinuity? So we need to draw a little bit. X squared plus 2, you know this is a parabola. X squared is a parabola. Lift it up 2 units. So you have taken the parabola, lifted it up 2 units. Okay. So notice I'm trying to go through each one of these functions. What is -5? Well, y equals -5 is a constant function, -5. Okay, which applies at one number, -3. The third function is a line, slope -4, y-intercept 2. Negative slope, y-intercept 2. All right. The next one is -5x over x minus 3 quantity squared. I had to use computers to draw this. But the point is, at 3, I have a vertical asymptote. Of course, because that's in the denominator. And x minus 3 is not a factor upstairs, so nothing is going to get cancelled. So the denominator factor survives, which means it will contribute to a vertical asymptote. Okay? When x is 0, I hit 0, mind you. But I'm going to -infinity coming from both ends. The next one is an interesting function. While it has a denominator, notice denominator can never be 0. In other words, this function does not have a vertical asymptote. Moreover, look at x. I'm squaring it, adding 1. So this quantity is always going to be a positive number. Okay, so that's how it looks like. As x gets larger and larger, denominator gets larger and larger. So I'm getting close to 0, but I never touch 0. I definitely don't go down. So that's the graph of 1 over x squared plus 1. So now these are 5 different functions, 5 different graphs I gave you. But you want to take pieces of each to construct this graph. All right. To the left of -3, I'm going to take a piece of this. This was a parabola. It goes on. Okay. So to the left of -3, I have that parabola. At -3, I have height -5. So at this point, I have height -5. To the left, I have this. And that's why that's an open point. What happens to the right of 3? To the right of 3, I have to use this line until 0, including 0. So when x is 0, I get y-intercept 2. So from this point to this point, notice this is an open point. Why is this open? Look at that. -3 less than. Okay? When x is equal -3, I am -5. So you see there is only one point per x coordinate. That's what makes it a function. Vertical line test has to pass. So I come from above, there is an open point there. My value here is -5. Then that's an open point. The next points come here. After 0, I have to resort to this function. This function, remember, had a vertical asymptote at 3. So from 0 to 3, I have a vertical asymptote. And after 3, including at 3, I'm using this function. So from 3, I'm taking that piece and I have drawn it here. Okay, height is very small. Okay, when x is 3, height is plug in 3, I get a 9 plus 1, 10 in the denominator, 1 over 10. So from that height onwards, from that height onwards, I go down. So this is the graph of f. What kind of discontinuities? Where do I see breakpoints? Here is a breakpoint, here is a breakpoint, and here is a break point, right? My function is broken. 1, 2, 3, 4, and a small point here. At -3, what kind of discontinuity it is? From here I'm jumping. From here also I'm jumping. Whereas here I'm going to infinity. So that's an infinite discontinuity. These are jump discontinuities. Okay. So the first two are jump discontinuities. And the third one for me is an infinite discontinuity. All right. Next one. Okay. Limit x approaching infinity, radical. If I plug in infinity, mind you, I'll get square root of infinity minus 8 times infinity, another infinity. Infinity minus infinity is a bad case. Infinity minus infinity, it's not defined. It could be 0, assuming they are both very close, or it could be plus or minus infinity. We don't know. This is undefined. So something like this requires simplification. Again, radical minus. Take its conjugate, radical plus. So I'm writing this as a fraction and taking its conjugate upstairs and downstairs. Why do we do that? Why do we take conjugates? To use difference of squares. Square of the first minus square of the second. Okay, always we choose conjugate so that you can take difference of squares formula. Denominator, I haven't changed anything. See? All right. Numerator is a difference of squares. Square of a square root, they go away. I'm left with 64x squared plus x minus square of 8x, 64x squared. That's wonderful. 64x squared and 64x squared go away. All I have is x upstairs. Downstairs, this requires some work. I can get 64x squared common. You will see in a minute why. I'm pulling out 65x squared from the expression inside radical. So I'm pulling out 64x squared from the radicand. When I pull it out, I have 1 here and a plus, that should be an x, okay, over 64x squared plus 8x outside, okay. Now I'm going to positive infinity. So square root of x squared is x when x is positive. So square root of this x squared is simply x. Square root of 64 is 8. And this is x cancels one of the x's. I should have 1 over x. All right. Fine. Now when I take limit x approaching infinity, oh, I haven't finished it. I still have an x upstairs. But look, there is an 8x here and an 8x here. This is why we did this particular simplification. I can get 8x common from the entire denominator. 8x comes out, radical stays in, and plus 1. X cancels the x. I have 1 over 8 and this expression. When x approaches infinity, this particular fraction goes to 0. That x cancels this x. I'm left with 1 over 8, radical 1, and plus this 1. 1 over 8 times 2, 1 over 16. Okay, until next problem.